Right. So we will start by revising reductions once, which we did yesterday. We'll be looking at a few more examples. I think I have taken 4 examples, which we'll see today. And then we'll move to approximate and randomized algorithms. Okay, so looking at the definition of reductions again, problem y is polynomial time reducible to problem x if having the solution of x, one can find the solution of y in polynomial time. So basically, once you have solved x using that solution, it takes you only polynomial time to find the solution of y. There are no constraints on how much time is taken to solve the problem x. In fact, there is no guarantee that x is solvable. There is no guarantee that you know a way to solve x or that you have the solution to x in hand. All that is being said is if you have the solution for x, using that, you only need a polynomial amount of time to be able to solve y. That's what we mean when we say y is polynomial time reducible to x. So the idea is the problem of solving y gets reduced to the problem of solving x plus some polynomial time operations. So we'll look at a few examples. So the first thing we're going to do is reducing independent set to clique. So given a graph G is equal to V comma E, where V is the set of vertices and E is the set of edges, a clique is defined as a subset of vertices again, such that every pair of vertices is connected by an edge. So if you remember independent set, it is a subset of vertices where no two vertices in that subset should be connected by an edge. Clique is the exact opposite. Every two vertices in your subset should be connected by an edge. So let's take an example graph. Call this A, B, C, D, and E, for instance. So let us say my graph looks something like, let's say this. So can someone give me a subset of vertices for this graph which forms a clique? It does not have to be maximal, minimal, anything, just a subset which forms a clique. Obviously, not a
ABC.
singleton set. Sorry?
ABC.
Yeah, A, B, C is one option. A, B, and C, all every
C,
pair
D,
exists.
E.
Yeah, C, D, E. You can take B, C, D, I guess that's another option. So on and so forth. These are examples. So we know what a clique is right now. And we already know what an independent set is. So coming back to the question, a clique is defined such that every pair of vertices is connected by an edge. Now reduce independent set to clique. That is the first question. So what are we supposed to do? Part A, show that independent set is polynomial time reducible to clique. What does this mean? You have a black box which can take a graph and give you a clique. Using this, how will you find the independent set for a graph? That's the question. Like show that you can find the independent set for a graph using this black box. That's the question. So do you guys want time to think or do you want me to explain the answer? Does anyone have a guess, a partial idea or like a starting point of what you think could be the way to go about this? Okay, we'll see. So reduce independent set to clique. So you understand the question, right, everyone? Is the question clear?
Yeah.
Okay, so we'll take the same graph. B, this was C. I think this was D. This was E. We had this and this, right? This is the graph. So I think A, B, C, this is graph G. ABC is a clique in your graph G, right? So now, um, let's draw the graph G complement or G dash. So what is the complement of a graph? All of you have studied discrete math, right? Someone define the complement of a graph. Okay, it's basically wherever you have an edge in G, you will not have an edge in G dash. Wherever you don't have an edge in G, there you will have an edge in G dash. It's just the ulta of the graph. So A, here it's connected to B and C, so it will not be connected to B and C. Instead, A will be connected to D and D. B is connected to A, C, D, so B will only be connected to E. C is connected to all four, so C will not be connected to anyone. And then D will be connected only to A. I think I made the connection. E is connected to C and D. So it should be A and B. E to A, E to B. Right? This is your G complement. Right? So does everyone understand what the complement of a graph is? In G. Now, if you look at A, B, C in G dash, you will notice that they form an independent set in G dash. There is no edge between AB, no edge between AC, no edge between BC. So, and this will hold for any graph you take. For, as of now, we are dealing with undirected graphs. G. A click in G will be an independent set in G dash and vice versa. A click in G dash will be an independent set in G. So let's see why formally. So you have a click in G. Let's say there are two nodes U and V. It means they are connected by an edge. There is an edge U to V in G. It could be V to U also, the graph is undirected. So when I say edge U to V, it means an edge between U and V, right? So for any pair of vertices in the click, there is an edge in G, right? That is why both of them are there in the click. So now this means in G dash, U comma V will not be connected by an edge. This means U comma V belong to independent set in G dash. Does this make sense to everyone? If they belong to a click in one graph, it means they are connected in that graph, which means they will not be connected in the complement of that graph, because that's what a graph complement is, or the inverse of a graph, whatever you call it, which means they will belong to the independent set in that graph. So is the relation between click and independent set clear?
Yeah.
Right. So using this fact, how do we exploit this property to solve independent set using click? So now what do I have? I have a black box which will take a graph as input. And give me the click as output, right? I want the independent set of G as my output. Now, the independent set of G is the click of which graph? G complement, right? So you simply put G complement as your input. You get back the click of G complement from this black box. And that very same set is your answer. It is your independent set of G. So if I have a black box that can find click of a graph. I want to find independent set of G. I use the black box to find click of G dash. Now, click of G dash is equal to independent set of G. So what's happening here is, this is the black box is solving problem X, which is the click. Now this is, once X has been solved, we need to do a polynomial time operation to get a solution of Y. And what is the polynomial time operation? There's no complement, no inverse, no transpose, nothing. It is just equal to. Whatever you get, you directly return that as the output. So this is how you reduce independent set to click. Is this part clear, everyone? Is everyone following?
I have a small doubt here. I understood everything that you just said, but we are
Okay.
saying that the independent set is polynomially, like in polynomial time, you can reduce it to click, right? Here we
Right.
used that clicks complement to show that you get the independent set,
We
right?
used a click to get the independent set. Correct.
Yeah. So you're not using the independent set and reducing it and getting the click, no. Here, what we did was we used the click and then reduced it to get the independent set.
Okay.
So how are you
I get
saying
your
that?
question. How is it independent set reducible to click
Yeah,
and not vice versa? Okay, right. Okay. How do I explain this? Give me a minute. Uh, Okay, so let's say you are working on a project. So there are multiple stages. You did a literature survey first, and then you built a model, you deployed it, you did some training, fine-tuning, implementation. You got your results, and finally you have to write a report document and submit it. Now, this is a team project. There are some 5, 6 people in your team. You are splitting your responsibilities initially, and you are volunteering to do the report and documentation work. You're saying, if you guys can take care of everything else, the literature survey, the implementation, training, all of that, the documentation fully is my responsibility. You're saying this now. So now, once all the implementation has been done and your teammates give you the results, you're going to take the data they give you and use it to write a report. Correct? So now the bigger problem at hand is to get the project fully finished and to get the grade. And your sub problem is to write the report. So if this division of responsibilities has been accepted by your team members, will you say the problem of doing a project has been reduced to the problem of writing a report, or will you say the other way around?
uh, like, can you just repeat the last thing that you said? Did you say that the
You
and
understand, there's a project,
yeah, I
every
understood
other
the other thing.
responsibility has been taken up by someone. You only have to write a report.
Yeah.
So essentially, your to-do list
My
initially
problem
was
is
your what was on your to-do list initially is this big project. What is on your to-do list now is just the
now it's
report.
just a report. Yeah,
So the problem of in doing a project has been reduced to the problem of writing a
report.
report.
Yeah,
How someone else is doing the implementation, you take that and you are just doing the documentation part. Similarly, the someone else is finding the click for you. You take that and you are just using it as an independent set. So the original problem you had was independent set. Someone else is doing the click part for you. You're taking that and logically you're just proving that click of G dash is equal to independent set of G. So the problem of finding an independent set got reduced to the problem of solving click And then you just have to show that click in G dash is equal to independent set in G or vice versa.
Oh, okay. Okay, fine.
Makes sense?
Yeah.
Any other questions, anyone? Okay, I assume everyone is clear. So yeah, coming back to the same question, there is a part B which says, well, first reduce independent set to click. Now prove that click is NP complete. So if you remember, yesterday we looked at how to prove NP completeness. There are two things you need to do. One is show that the problem is verifiable in polynomial time. Right? So what is the click problem? It is a subset of vertices. Every pair should be connected by an edge. Supposing I give you a click, or I give you a subset with k vertices. What is the, how long is it going to take to verify whether it is a click or not? So we have to take every pair of vertices. Let's say you have k choose 2 vertices, and you have to go to the adjacency matrix or whatever and look up, right? So k choose 2, I think, is going to be k into k minus 1 upon 2, which is approximately k square, right? So you can say it is order of k square. So is this, if I give you a subset of vertices, it is going to take you roughly order of k square time to verify whether it is a click or not, which is verifiable in polynomial. Does everyone agree? Yes?
Yeah.
Okay. The second thing was you have to prove that click belongs to NP hard, for which we have to say all of NP is polynomial time reducible to click. This, yesterday we saw it is difficult to do this directly. So what we do is we take some known NP complete problem. We know that all of NP is reducible to some NP complete problem. Now, if you can take this NP complete problem and show that it is reducible to click, then by transitivity, your all of NP is going to be reducible to click, which means click is NP hard, which means it is NP intersection NP hard, which is NP complete. So that is exactly what we did in part A. So the NP complete problem we have taken up is independent set. So independent set is known to be NP complete. This part is given to us. And here what we did in your subdivision A or subdivision 1 is you proved independent set is reducible to click. So by transitivity, all of NP is reducible to click. Therefore, click belongs to NP hard, which means it belongs to NP intersection NP hard. Therefore, click is an NP complete problem. Clear? Any questions? Yep. Okay, we'll do another example now. The set cover problem is defined as given in the image. Given a universe U and a collection of non-empty subsets, a set cover is a collection of some or all of the above subsets such that each element of U is covered at least once. We'll understand the set cover problem first. So my universe is going to be, let's say 1, 2, 3, 4, 5, 6, 7, 8. I have 1, 2, 4, 5. Let's say 2, 6, 7. S3 is going to be 3, 8, 1, 2. S4 is going to be 1, 4, 5, 7. You have 4 subsets, 4 non-empty subsets, which need not necessarily be of the same length. Now, I have to pick some of these subsets some SOME of these subsets such that all elements in the universe are covered. So can someone give me an answer? Like, you can pick any number of these subsets, preferably minimal number of subsets required, such that every number from 1 to 8, which is every number in the universe, should be there at least once. So the union of the subsets you select should be the universe. That's the idea. Can someone try?
S1, S2, S3.
Yeah, S1, S2, S3. If you take, you have 1, 2, 4, 5, again 2, 6, 7, 3, 8, 1. Right? So this is an example of the set cover, I think. Yeah, set cover problem. So is the problem definition clear to everyone?
Yeah.
Right. And the other problem we will be considering in this segment is vertex cover, which I believe everyone is familiar with right now. So the question is, I think, reduce vertex cover to set cover. So, okay, before we go to the solution, one of you tell me in terms of the machine analogy give you have a machine which solves this problem, use it to solve this problem. So tell me, uh, we, uh, we have a machine right now. Which problem does it solve and which problem do we want to somehow solve? What I'm trying to ask is I want
Solve
to see.
set cover, no? Something.
Correct. So you have a machine or a black box for set cover. Exactly. Black box for set cover problem. So using this, can I somehow find out the vertex cover? That's the question. So is everyone clear with the question?
Yeah.
Okay. So any guesses, any ideas? It does not have to be a complete algorithmic explanation of this is how you reduce. Like, do you have a starting point, a vague idea of how to go about this? Anyone?
Oh, wait, I have a doubt.
Mm.
Like, so the black box will now, like, if we give a couple of subsets, it'll tell whether it's like they cover
No,
all these subs.
you give it the universe. You give it S1, S2, up to whatever subsets you have. You give it all of that. It will give you the selected subsets such that all the elements in the universe are covered.
Okay. Yeah.
So using this, you have to find the, one second. Use this to find the vertex cover of a graph G. Any ideas?
Does
Okay,
it use
so
intersection or something?
how? Intersection of, okay, intersection of what, first of all?
Of that subsets, the selected subsets. Because then
Okay.
you'll get that element that is repeating in like each thing, and then I don't
Okay,
know.
what are your inputs to the black box? What is your universe and what are the subsets?
The universe would be all the elements that are there, and then the subsets it chooses is the set covers, no?
That is how the black
Black
box
box
works.
works.
But
Yeah.
what is the problem given to me? Problem given to me is G is equal to V comma E. I don't have U, S1, S2, etc. You get it?
Yeah.
Because whoever has given me this task, they have a graph, they want the vertex cover. So they're only going to give me the graph, the vertices and the edges. So if I have a set cover machine, I have to transform this graph into the kind of input which the set cover machine takes. So what is the input going to be? So that transformation is the key idea of the reduction here. If you looked at
Vertices,
the
no?
The vertices
Are the universal, like,
very good, correct. So your let's say you have no, okay, wait, vertices are no, not exactly. Good try. You were very close, but not exactly. Okay, I'll explain. So before I explain the answer to this one, so this previous thing which we saw was easier because click independent set. Both of them are problems which deal with graphs. They take a graph as input. They give a subset of vertices as output. Both of these. Only the property of that subset is going to be different. A click is something else, an independent set is something else. But the input output data types, loosely speaking, are the same. In here, that is not the case. So here, vertex cover, the input is a graph and the output is a subset of vertices. For set cover, the input is going to be a universe and some subsets. The output is going to be a collection of subsets. So we have to transform what we have in hand into what is suitable, what is a suitable input for the machine. Only then the machine will work, right? So that is one thing we have to keep in mind. So I'll tell you yes.
I think the universe should contain all the edges.
Very good. Exactly. Universe is going to be E1, 1 second. E1, E2 up to EK. Let's say you have K edges totally in your graph. The universe is going to be all the edges. Why? Can you tell
Because
me?
they must include, because it's gonna give us a result that will include every edge.
Exactly. And in vertex cover, for every edge, you need to have at least one
one.
endpoint, right? So your universe is going to be edges. Exactly. That's the thinking we are looking for. Right. Now, what are the subsets going to be? So for every edge in vertex cover, what are we picking? So vertex cover problem. When I come to this edge, when I am considering this edge, what am I going to do? I'm going to add at least one of the endpoints to my vertex cover, right? So for every edge, we are concerned with the vertices. So I'll tell you my idea. Tell me if that makes sense. So for every vertex, we have a subset. So for V1, we have a subset. S2 is a subset corresponding to V2 and so on. Let's say you have n vertices, then you have one subset corresponding to each vertex. And what is this subset going to contain? It has to be a subset of the edges, should be related to that vertex somehow. So how? Whichever edges are incident on that vertex, those will be considered in that subset, for example. Okay, so we'll take a small example and okay, this is the graph. I'm going to give names to these edges so that it becomes easy for us to identify. This is 1, this is 2. These are not weights. It is just a naming thing, a name for the edges. Or, oh, okay, I can call them A, B, A, C also, right? Okay, so what's my universe here is all the edges, right? A, B, A, C, A, D. And then we have B, C, B, D, CD. Have I covered everything? Hopefully, yes. Right. So now for every vertex, I am going to create a subset. And that subset is going to contain all the edges which are incident on that vertex. So for A, it will be A, B, A, C, A, D. For B, it's going to be A, B, B, C, B, D. For C, it will be A, C, B, C, C, D. And for D, it's going to be AD, BD, CD. Am I right? Am I making some mistake? No, right? You guys say something.
No, that's correct.
Right. Now this is my universe. These are my subsets. So now I have a universe. I have a bunch of subsets. I'll pass these to my machine. It is going to give me a few of these subsets such that all my edges are covered, right? So let's say I put all this in my set cover machine. Can you give me a sample output? What will it give for this case? There are multiple possibilities. Give me any one. One set of selected subsets. ABC works. A the
Yes,
AB
it works.
AC AD, AB BC BD, AC BC CD, AC BC CD, right? So ABC is one possible output. Now, what does this mean? We have selected some vertices such that all the edges in the universe are covered, and these vertices were selected based on the edges incident on them, right? So I selected these three now. It means I have taken into consideration all the edges that had at least one endpoint in this, and this. And when that is what is equal to my entire universe, it means these vertices, between them, they cover all the edges, which is exactly what my vertex cover is, right? Do you guys follow? Do you want me to repeat?
Akka, could you repeat?
Okay, how far did you understand? Which part do you want me to repeat?
I understood the part like you took
What
the
you get
yeah,
from
the
the set cover
ABC
machine?
is okay. Then after that, the way you put it together, that
Okay,
can you
right.
explain
So
it?
now what I'm saying is this ABC is our vertex cover. This is what I'm saying. And what is my reasoning behind that is essentially what was my universe? All my edges. What are my subsets? Every subset corresponds to one vertex. And what does the subset contain? All the edges which are incident on that vertex, right? Now, I'm selecting a few of these subsets. Let's say I'm selecting A, B, and C. It means the set cover machine is designed such that if it is giving you these three as output, it means these three subsets together, the union is equal to this. Am I correct? That's how the set cover problem is defined, right? Right.
Yeah.
So what this means is all edges incident on A, union edges incident on B, union edges incident on C is equal to my entire set of edges. Correct?
Yeah.
Now, A, B, and C are vertices such that for every edge in E, it is either incident on A, or it is incident on B, or it is incident on C, right? That is what this statement means, putting it alternatively. And that is exactly what a vertex cover, what the definition of a vertex cover is, right?
Yeah.
So whatever you get from your set cover machine is your vertex cover directly.
Yeah. Thank you.
Does it make sense to everyone?
Yes.
Okay. So how do you reduce vertex cover to set cover? Your universe is the set of edges in the graph. You have one subset for each vertex. Elements of that subset are going to be edges incident on that vertex. And if you give this to your set cover machine, the output you get is directly going to be your vertex cover. So, okay, is that clear?
Yeah.
Okay, we'll go to the next example. Any questions so far? Okay, I assume there are no questions. So the next thing is going to be reduce Hamiltonian cycle to traveling salesman problem. So Hamiltonian cycle is you have a graph. You want to find a path that visits each vertex exactly once, and finally you have to return back to wherever you started from. That's Hamiltonian cycle. And TSP, of course, you have a bunch of cities. They're all connected to each other. In this example, we will assume it's a fully connected graph for simplicity. There are weights for every connection, and you want to visit all cities at least once, right? So, of course, in TSP, in your optimization version, there is an additional constraint that if your weights represent something like the cost, you have to minimize the cost. All of that is there. But we will not go into that much complications right now. For now, it is you have a graph, you have vertices, which are like cities or towns. You want to visit all cities. So just by looking at the problem definitions, you can sense that there are similarities, right? So the only thing is here, TSP is a fully connected graph. For your original graph in your the graph given to you for Hamiltonian cycle, it need not be fully connected. So we have to use a TSP solving machine to get a Hamiltonian cycle. This is the question. Is this clear?
Yes.
Any questions? Okay, let us assume this is the graph G given to me. Okay, wow. For this, I want to find a Hamiltonian cycle. I don't know if a cycle. Okay, wait. Okay, then let this be the graph. Now I'm pretty sure a cycle. Okay, never mind. Doesn't matter whether a cycle exists or not. So this is the graph given to you. For this, you have to find a Hamiltonian cycle if it exists. So, and you have to use the TSP solving machine. Now, the thing about your TSP solving machine is it takes a graph as input, but it should be a fully connected graph. Meaning every node should be directly connected to every other node. That is the constraint given to us. And it will give you a TSP tour or path, whatever you call it, as the output, right? So now this graph I have here is not fully connected. So what do I do? So if I had a fully connected graph, I would give it to my TSP machine. It will give me a TSP tour. From that, somehow I can try to find a Hamiltonian cycle. But this graph is not fully connected in the first place.
Should we find the click of the graph?
That will give you a subset of vertices. But you want to visit all the cities here, right? Not a subset of the cities. You get what I'm saying?
Yeah, yeah.
So what we can do is you simply add vertices here. I'll tell you how that makes sense. So this one is going to everything else. This one on the 1, 2, so 3, 4. This one has 1, 2, 3. So I think this should go here. This has 1, 2, 3, 4, 1, 2, 3, 4. Right now, this graph is fully connected. Now, the extra vertices which I have added in a different color for a reason. Now, what we'll do is we are going to give weights to these vertices. So, weight from U to V, weight of a vertex of an edge, weights to the edges. I'm sorry. Weights from U to V are going to be 1 if it is a green edge, 0 if it is red. In other words, if the edge was already existing in the graph given to me, then that path cost or weight is going to be 1. And if it is an edge, I have added simply to modify my graph to make it suitable for this machine, then that weight is going to have a cost of 0. Okay, so this is the rule I am framing. So now I have a fully connected graph, right? Yes?
I have a doubt.
Yes.
Shouldn't the red ones be higher than the green?
It doesn't matter, and I'll tell you why, but you can take it vice versa also. You can take 500,000, you can take random values. As long as you
Okay.
remember what value you're assigning for greens and what value you're assigning for red, it doesn't matter. We're not going to do anything with the actual, like, it's not like a penalty kind of a thing. You will come to know when I tell you what we're doing with the weights. So as of now, we have a fully connected graph. We have a way of differentiating which are the edges that were originally there, which are the edges which I have added to make this suitable for the machine, right? Now I will take this graph. See, world-class graphics, guys. Everyone look at this. You take this graph, you feed it to the TSP machine, and it is going to give you a tour or a path as output, something like, let's say, A, B, X, Y, A, whatever, something it's going to give you, right? The TSP machine is going to find the TSP tour and give it to you. Now, you will check the values of all these edge weights. If all of them are green, meaning if all are ones, it means we only used the edges which were already there in my graph, and we got a TSP tour, right? And a TSP tour there is just going to be all cities visited exactly once, and you come back to your starting point. So that is exactly what your Hamiltonian cycle is going to be. Whereas if there is a 0, or if there are zeros, if there is even 1 0, it means there is a TSP tour in this graph, or it is possible to visit every vertex exactly once and come back where you started, but only if you are willing to go through some of these roads which you created, which were not existing. Which means in our original graph, there was no Hamiltonian cycle. So in that case, you would say no cycle exists. CYCLE. So this is why I said it doesn't matter whether red is 0, green is 1, or vice versa. You just need a way of differentiating red from green. The numbers are completely arbitrary. So do you guys understand? Do you want me to repeat it once?
So is this how we are meant to write it even in the exam, like create our own thing and then say if like this is the case, then it's like this. If there is a red,
Yeah, I
then it
mean,
doesn't exist.
you have to write it neatly, of course, but
Oh,
other than
that
that,
is
other
okay.
than that, yeah, you have to write a story only.
Okay. But if they ask something that we haven't seen, how are we meant to think of all this? Like in
There is
general.
a slide for that. We will come to that.
Oh, okay, cool.
Okay. This question, do you all understand? Is this clear?
Okay, I have
Or
a
do you
doubt.
want me Yes.
The first graph, the green color nodes with the green color edges graph,
Mm,
that's a Hamiltonian cycle already, and we took
mm.
the weights of that as 0.
Oh dear. Okay.
Is it? No?
No, what I have done is for the existing, the edges which are already existing, I've taken the weights as 1. For the ones which I created, I've kept it 0. But it can be interchangeable also. It doesn't matter. Anyways.
Okay. So if we take and if we give the red color edges as 1, and
Okay.
later when we try to the complete that new thing which we added edges, if we try to find a TSP there,
Hmm.
uh,
This
The
condition will change. So this will become a 0, this will become a 1. That's all.
that is fine. Will it be? Is it mandatory that it should be all zeros and all ones? Because there might be a root which inserts people
Some
between
edges which are already there and some edges which you have created, right? That's what you mean, right?
the cost of the tour should be less than or equal to k.
No, again, it goes back to how you have defined your problems. How
Problem.
I have defined TSP is this machine will take a fully connected graph and give me a tour. It need not be the
Okay.
best tour or anything. So yeah,
Okay,
if
okay.
you define your TSP like that, then your reduction logic will change
Okay, got it.
accordingly. Okay, any other questions? Okay, we'll do one last example of reductions. This is the idea of reduction using gadgets. So all the reductions which we saw so far were don't come at me for saying this, but the textbooks call them trivial reductions. I know it did not seem trivial, but trivial in the sense that you simply had to exploit logical properties of the two problems given, and you have to say something like, okay, if it's a click here, if I take the complement of the graph, it is going to be independent. So it is just a logical property which you had to think, identify, prove, and it was done. You didn't have to like do some construction or create a new structure per se out of nowhere. So those are called trivial reduction. So the reduction we'll see here, you will have to create a new entity of your own. So such reductions are called gadgets. So this was not taught during my time. For you guys, I saw it on the slides made by a faculty, which is the only reason I'm teaching this. I am 99% sure you will not get a gadget-based reduction question in the exam. That is an unseen question. I mean, whatever is there in the slides, of course, the faculty might ask. A new reduction question like reduce problem X to problem Y, where a reduction is involved, generally they won't ask it in the exams because, like developing a gadget and stuff, it takes a lot of time to think. It's not fair to put that in a 3-hour paper. So if this does not make too much sense, it's okay. Or if you're not able to solve questions using gadgets, it's okay. I just wanted to start with that caveat, right? So we're going to reduce vertex cover to Hamiltonian cycle. Write that down. I'll forget what I'm talking about. Vertex cover to Hamiltonian cycle. So this reduction, it's apparently it cannot be done trivially just by exploiting properties of vertex cover, properties of Hamiltonian cycle. You cannot say, oh, I take the complement of this, I take the transpose of that, I'll get this. And the Mari, it is not possible. So we have to come up with something called a gadget. So for every edge U to V in our original graph, we are designing something called an edge gadget, which looks like this. The edge gadget again is a collection of vertices. These are your vertices, and these are connections between them. Don't ask me why it is defined in this shape. I have no idea. Only the person who invented it knows. Now we will use this edge gadget to solve the Hamiltonian cycle problem and get a vertex cover as a solution. Right, so are we clear so far? For every edge, we are coming up with something called the edge gadget, which looks like this. How to use it, I'll tell you, but are there any questions till now?
Okay.
Okay, so now this is the graph for which we want to find the vertex cover by first using the Hamiltonian cycle technique. So what we're doing is, for every edge in this graph, we are replacing it with an edge gadget. So if you see, this is the VY edge. So you're drawing the edge gadget for VY there, V dash, YY dash. This is the VU edge. So you have VV dash, UU dash, VZ. So VV dash, ZZ dash. Similarly, UW, the corresponding edge gadget is here. UX, the corresponding edge gadget is here. So you are constructing a graph made only using edge gadgets such that for every edge in your original graph, you have a corresponding edge gadgets. Now this is the graph we have constructed. Are we clear so far?
Yes, Akka.
Now, what we'll do is we are going to perform the Hamiltonian cycle operation for this newly constructed graph. We're going to find the Hamiltonian cycle of this graph. And when I say Hamiltonian cycle, it has to pass through every vertex of this graph, which means obviously it will pass through each edge gadget, right? Because the vertices are basically part of an edge gadget. This vertex is part of the VY edge gadget. This one is part of the UV edge gadget. This one is the UW edge gadget and so on. So every vertex is part of some edge gadget. So if I'm passing through every vertex, I am obviously passing through every edge gadget, meaning I am considering every edge, right? Because every edge gadget corresponds to every edge. Now, what I want to do in vertex cover, for every edge I consider, I have to pick at least one of the endpoints. So let me do just that. Whenever I enter an edge gadget, whichever side I am entering, this is the V side, this is the U side. So whenever I enter an edge gadget, whichever side I'm entering through, I will make a note of that. And I will continue on my Hamiltonian cycle, right? That's what I'm going to do. So we will do that here. I'll take probably yellow color. So I will start from here. Is it visible? Are you able to see the thing I'm drawing on the diagram? So yeah, this edge gadget, I went in and I came out. I entered through the V side. So I will note down V. Now, next I am continuing through this edge gadget. Again, it's through the V side I am entering. So V is already noted down. Then I come to the third edge gadget. Again, it is through the V side I am entering. So V is still noted down. So if you see now, we have covered this edge, this edge, this edge, and what I've noted down is V, right? And after that, we proceed this way. Now this edge gadget, I am entering through the U side. So let me note down U. And that was UX. So this has been taken care of. Now I continue with my cycle, Hamiltonian cycle. This again, this edge gadget, I'm leaving now, so I don't have to make note of anything for VU. And then I'm again entering this through the U dash, which is the U side. So U again, I've made note, and that was for the UW edge gadget. So now if you see what are the things I've made note of, V and U, and all the edges are covered. So I have a vertex cover, and my vertex cover is the set of nodes V and U. This is how we use edge gadgets to reduce Hamiltonian cycle to vertex cover. I'll repeat what we just did. I'll give you a summary kind of thing. So aim is use Hamiltonian cycle to find vertex cover for a graph. Now it turns out this cannot be done trivially. So for every edge, you develop an edge gadget, which is again a graph. It has nodes, it has these particular connections. It has a U side and a V side, and it looks like this. Now we are going to construct a new dash. Let's say I call this G1. If this graph is G, let's call this G1. Where in G1, for every original edge, you put the corresponding edge gadget. Now that is the construction we have made. Now what I'll do is I will find the Hamiltonian cycle for G1. Hamiltonian cycle by definition has to pass through every vertex of G1. Meaning obviously it has to pass through every edge gadget of G1 because the vertices are part of edge gadgets. So every time it passes through an edge gadget, whichever side it is entering, I will note that side down. So for here it was V side, here again V side, here again V side. And then it comes here, it was U side. This is this edge gadget. This part is leaving. It's not entering, so I don't need to note it down. This one again, it's the U side. So VU. Now, what happened here is for every edge gadget basically corresponds to an edge, right? So when I am looking at this part, I'm basically looking at the VY edge. So this one, I'm for this, I am noting down this edge. Next, I'm going to VU. For this edge also, I'm noting down this vertex. Next, it is VZ. For this edge also, I've noted down V. Similarly, for every edge, I'm noting down one of the endpoints. So that is exactly what my vertex cover is. So here we get the vertex cover. So is that clear?
Yeah, I got the vertex cover part. Where are we finding the Hamiltonian for this graph? Like we didn't like, it's just all the gadgets put together and then we found the vertex
This
cover.
is the graph, and you are finding the Hamiltonian cycle, as in you want to visit every vertex exactly once. So you are traversing it as a Hamiltonian cycle. Now for this graph, you could also have, wait, there are, so there are these intermediate connections. You could have gone like this, like this, like this, like this, come back. Ipdiyo you could have traversed the graph, yeah. But we are going particularly in this shape because we want to visit every vertex exactly once. So we are traversing along the Hamiltonian cycle.
Okay, got it.
Got it? Any questions?
I have one.
Yes.
Bottom view, top view, V dash and V, you're connecting it when you're drawing it, but in the diagram, they're not connected.
So it is Hamiltonian cycle find பண்ணணும்ல.
ஆமா.
So அதனால that is an assumption we make. So
Okay.
the thing is, within an edge gadget, இப்போ இந்த edge gadget இருக்குல்ல, so இதுல இல்லாத connections you cannot make it. இப்போ இங்கேக்கு இங்கே இந்த மாதிரி connections you cannot make. But across gadgets, for the sake of finding a cycle, you are allowed to make connections.
Okay. So across two gadgets, we can connect.
Now, within a gadget, it has to look like this.
Okay.
Any other question?
This edge gadget is only for this question, right? The thing
Yeah,
is,
yeah,
the
yeah.
template is only
Yeah.
for this question. Okay,
Yes,
cool.
yes. And so the idea is all reductions will not be trivial. எல்லாமே வெறும் லாஜிக்கலா யோசிச்சு பண்ற மாதிரி இருக்காது. Sometimes you will have to construct something also. அந்த satisfiability problem to vertex reductionக்கு அதுக்கு ஒரு gadget பண்ணுவாங்க. That's one big graph like thing. So there are different gadgets. அந்த மாதிரி questions மோஸ்டா எக்ஸாம்ல you will not be asked mostly. But இப்படியும் something exists we are supposed to know. That's the reason I put this. Okay, shall we move on? Okay, so yeah, இதுக்கப்புறம் I'm going to take approximation and randomization algorithms, but அதுக்கு முன்னாடி just a few like things which helped me work on reduction questions. So if two problems are given, identify which must be reduced to which. So this, I think one of you had a question initially when we were discussing independent set and vertex cover. Why is it this reduced to this and not the other way around? So அது வந்து we have to be careful, especially இந்த NP complete prove பண்ண சொல்றப்போ what we are supposed to do is take another problem y and show that y is reducible to x. But intuitively it might seem like எனக்கு வந்து x NP complete னு prove பண்ணணும். So நான் x எடுத்துட்டு x reducible to y அப்படின்னு prove பண்ணிடுவேன். It like ஒரு muscle memoryல people tend to do that. So there you have to be careful. Which am I reducing to which? Depending on என்ன கேட்டிருக்காங்க or எனக்கு என்ன தேவை. That is one thing. If two problems are given, if one problem is given and say you are asked to prove NP completeness, again as I said, choose the second problem wisely. It should be known NP complete and it should be in some way connectable to the given problem. So for example, உங்களை வந்து prove that vertex cover is NP complete அப்படின்னு சொல்லிட்டாங்க. So first thing you'll do is அது verifiable in polynomial time you will prove. எனக்கு ஒரு subset கொடுத்தா v vertices இருக்கு, நான் வந்து v square or v cube whatever I can check whether it is a vertex cover. So it is verifiable in polynomial time எழுதிருக்கும். When you want to reduce an NP complete problem to vertex cover, independent set எடுத்தீங்கன்னா easy. Pannidalam, we know. Click edta, it is also trivial. You will have to think of the logic, but click is easily reducible to vertex cover. I think partition problem one irukku, subset sum நேத்து பார்த்தோம்னு நினைக்கிறேன். I'm not sure. All of those are trivially reducible to vertex cover. அதெல்லாம் விட்டுட்டு if you take in the Hamiltonian cycle and I am going to reduce it to vertex cover, now you are in trouble. So it should be intuitive, or you should be able to form a connection between the problem you are choosing and the problem you are given. The next thing is look for similarities or contrasts in the definition of two problems. Ipo set cover, vertex cover எடுத்தீங்கன்னா, when I was explaining that example, one of you said very beautifully, the universe has to be all the edges because in vertex cover, we are considering all the edges. That one line is the essence of that entire reduction. அது மாதிரி independent set and clique எடுத்தீங்கன்னா, independent setல no pair should be connected, cliqueல every pair should be connected. So they are stark contrast. So you'll take a complement or an inverse kind of operation. So if you are able to identify some such relationship, that is the crux of the reduction. So look for that. Other vechi, you define how the solution of one problem can be used to obtain the solution of another problem. This is how reductions work. Clear so far? Any questions? Okay,
Yeah, clear.
shall we? Sorry, someone was saying something.
Clear.
Okay,
Akka, could you please show how 3-sat problem can be reduced, like polynomial time reduced to something else? Because it's been used a lot for examples.
வந்து gadget use பண்ற மாதிரி தான் இருக்கும். I have not gone through it. You text me after the meeting, maybe I will like look at the slides and I'll get back to you. You know, it's a gadget based reduction. படிச்சிட்டு தான் I will be able to explain.
Yes.
Okay. Anything else? Sorry. Shall we move on to approximation now, or do you guys want like a 5-10 minute break? I have approximation and randomization algorithms to teach. Rendo சேர்த்து total we have some 40 slides, I guess. It will not be in the reductions மாதிரி ரொம்ப heavy-ஆ இருக்காது mostly. But yeah, do you want a break or shall I proceed?
Proceed, Akka.
Okay, sorry. We'll start. Before I go to approximation algorithms, I'll give you some context. So yesterday I was mentioning that I'll talk about deterministic and non-deterministic in the next session, right? So you might have been taught this in your earliest DAA classes itself. Deterministic algorithms produce the same output for a given input every time. So if this is the input, this is only going to be the output. நீங்க எத்தனை தடவை ரன் பண்ணாலும், எந்த சிஸ்டம்ல ரன் பண்ணாலும், what time of the day, what CPU, what operating system, irrespective of all that, what programming language, irrespective of all that, a deterministic algorithm will give you the same output for an input every time. Non-deterministic, not really. Between the first time you run and the second time you run, the output may vary. So can someone give me one example for deterministic and one example for non-deterministic? Deterministic?
To check if a number is even or not.
Odd even, very good. Example. No, okay, wait. To check whether a number is odd or even is a problem. What is your algorithm? What's the logic you're using?
If the remainder while dividing by 2 is equal to 0, then
okay.
return true, else false.
Yeah, modulo 2 odd or even check. Right, that is a deterministic algorithm. An example of non-deterministic. It could be, okay, I don't know how many of you know this. Or a polynomial expression இருந்துச்சுன்னா, there are different ways of finding the roots of a polynomial. IoT students, did you learn this in your first class? there are 2 points A, B. A, this is f of A, this is f of B. If the signs are opposite na, adukku nadula. Was this taught to you, IoT people?
Yes.
I remember. It was taught to me on my first play. So basically, there is one method to find the approximate root of a polynomial. So you take 2 points A and B such that the value of the polynomial at A and B have opposite sign. One should be positive, one should be negative. And then I think you will find the in the graph வந்து x-axis ல எங்க கட் ஆகும் கண்டுபிடிச்சிட்டு அங்க you will find I think f of that point C, I think. Again in the ரெண்டு point you will compare and the மாதிரி you will keep going back and forth. That algorithm is not the point right now. அதுல என்னன்னா you are reducing you're narrowing down your interval again and again until you finally converge at one point. So anga vanda the answer you get will be like close enough but not necessarily the same. So first time if you get 1.0003, next time you might get 0001, 0007 and the mari very small difference da irukum, but exact same answer irukadu. It might be different. So I think that's called the regular falsy method, and there is another Newton-Raphson method. You will learn these later. But yeah, so in the Mari, there are algorithms which will not give you the exact same output every time. Another example could be your what do I say? A random number generator. To some extent, actually, if you look at your like Python random function, behind that there is some deterministic formula written. But from the user perspective, it's giving you a random.randint. Every time it gives you a different integer. Yeah. So in that sense, that is non-deterministic. Right. So is that clear? Okay. So இப்போ எதுக்கு இத பத்தி பேசினேன்னா, with NP hard problems, which we saw yesterday, are the hardest class of problems to exist. It is not always easy to design a deterministic algorithm. Update design பண்ணிட்டாலும் to implement that and find the solution might be very expensive. For example, classic example, traveling salesman. You have a brute force algorithm, but that is going to be some n factorial or 2 to the power n something, which is very expensive even for small input sizes, right? So அப்போ வந்து we will go for algorithms which are approximate. They'll not give you the exact solution, but they'll give you a good enough approximate solution. Two things about such algorithms. One, they are non-deterministic. Whenever we talk about approximation, it is immediately by default non-deterministic, meaning might not give you the same answer every time. There will be a small plus or minus, not very far off the mark, but kuti deviations will be there. Secondly, when you say this is approximate, how close is it? What is the plus or minus error range? You have to quantify in some way. So these are the things. The reason for coming up with approximate algorithms is this NP-hard deterministic algorithms custom. And when you come up with an algorithm which is approximate, you need to quantify the level of approximation you're doing. Clear so far? Yes.
Yes.
Tab. Sorry, my bad. Now share this tab listed. Okay, can you see the approximation algorithms slides?
Yeah.
Is it?
Yes.
Okay, so இப்போ நான் வந்து before I go to the actual algorithm, approximation quantify பண்ணணும்னு சொன்னேன்ல. So we do that using something called the approximation ratio. It is going to tell you how close is my solution going to be to the actual solution. See, the whole idea of using an approximation algorithm is when you cannot find the actual solution, you're giving a rough estimate and saying this is close enough. So how close? What is the error? How far away, or what's the deviation expected, or what is a reasonable deviation between your solution and the actual solution? அப்படின்னு measure பண்றது தான் approximation ratio. An algorithm is an alpha approximation if optimal by alpha less than equal to your algorithm less than equal to optimal into alpha. So let OPT be the optimal solution. So adukku your optimal solution in terms of it could be optimal cost, optimal whatever. If a knapsack problem now, the maximum profit obtained by the optimal solution. Traveling salesman problem now, the minimum cost of the TSP path which you are choosing. And whatever is the numeric value obtained in the optimal solution, that is defined as OPT. And ALG is the numeric value obtained by my approximate solution. My approximate solution la knapsack la வந்து இவ்வளோ profit வருது. TSP la this is the cost. அப்படின்னா if you have a number alpha such that OPT divided by alpha less than equal to ALG less than equal to OPT times alpha, then you say your algorithm is an alpha approximation. So if your alpha is equal to 1, it means your optimal solution and your approximate solution are same, right? Which is theoretically possible, practically not possible. So the idea is bring your alpha as close to 1 as possible. That's the idea. Alpha will be greater than 1, but try to bring it as close to 1 as possible. That's the idea. So do you understand what approximation ratio is? Any questions? Okay. So we will look at one example of an approximation algorithm for vertex cover problem. We are looking at simple problems which we know how to solve so that optimal solution solution we can compare. That's the reason we are going for simple problems instead of something like TSP or whatever. Right? So this is one approximate algorithm. What it does is for every edge in your graph, you add both the endpoints to your vertex cover subset and you delete those vertices from your graph. So when you delete those vertices and the vertices length where media edges also get deleted. So it is like you take one edge, you take both endpoints, put them in the vertex cover. Now you delete those two endpoints as well as all edges incident on them. Then you take the next edge with another pair of endpoints. Repeat the same process, keep deleting until your graph becomes null set. Right? So this is the algorithm. Algorithm clear? Ellarkum?
Are U and V picked randomly?
Sorry?
Are U and V the vertices? Are they picked randomly?
Yeah, random order. In any case, ultimately, your final answer will be a vertex cover because நீங்க எந்த ஆர்டர்ல போனாலும் whenever you encounter an edge, you're taking both the endpoints and all edges which are incident on those endpoints, you're deleting. Again, you're taking the next edge and you're doing the same thing. So for every edge, at least one, and if possible, both endpoints will also be in your vertex cover set.
Okay.
Any questions so far?
Could you please show us with an example?
Okay.
Simple one.
Stop share. 1 second. A picture here. இதுல வந்து Control C, Control V. Okay. Okay. Now from here, where window. Can you see the screen now? The notes page.
Yes.
Okay, this is the graph. இதுக்கு vertex cover கண்டுபிடிக்கணும். So I'm going to start with this edge. So இப்போ நான் என்ன பண்ணுவேன்னா, I will put both the corresponding endpoints into my vertex cover subset. Now I will delete both of these from the graph. So when I delete A, what happens is இது delete ஆயிடும். This vertex gets deleted. This vertex gets deleted. When I delete B, this one also gets deleted, right? So இப்போ நம்ம கிட்ட என்ன இருக்குன்னா C, D. This is the graph I have now. Correct?
Yes.
Now அடுத்து இந்த edge எடுத்துப்பேன். Again, I'll put C, D. I delete this, I delete this, I delete the corresponding edge. My graph is empty. So now this is my vertex cover. Now, if you ask me, is this a valid vertex cover? Yes. For every edge in the graph, at least one endpoint is in the set. Is it the minimal vertex cover? Did we really have to take all 4? Not really. If you had taken, I think, A, B, C, it would have covered everything. So this is not the best solution. It's not the optimal solution. The optimal solution would be minimal vertex cover. The approximation algo. But it is it's an approximate solution. It is right, but it is not the best. Now, how far away from the best is it? Rather, we want to quantify. So is the algorithm clear?
Yes. And
Yes.
when we talk about vertex cover problem, we are not, it doesn't matter that we take the optimal solution, right?
Depends on decision version optimization version. So, இப்போ நான் சொல்றது வந்து when I say we are trying to solve NP hard problems, generally we are trying to optimize them, but you cannot find a deterministic algorithm which gives you the optimal solution. So, you want a close enough answer.
Oh,
நீங்க reductions பண்ணும்போது mostly decision versionல தான் deal பண்ணுவீங்க, or even if you're doing in like solve the problem kind of version நாலும் give me a solution அந்த மாதிரி தான். That is we'll be talking in terms of that only. But approximation algorithm னு வரும்போது the whole idea is I cannot find the optimal, so I want to find something that is close to the optimal. So அங்க வந்துட்டு a solution is not good enough. I have to prove that this is close enough to the best.
okay, got it.
Okay, so this is the algorithm. This is just another example. Okay, so இதுல வந்து proof. Yeah, this is what I was looking for. So இங்க பார்த்த algorithm வந்து இப்போ how close a bound is this அப்படின்னு பாத்தீங்கன்னா it can be proven that this is a 2 approximation. So your alpha value for the vertex cover approximation algorithm we saw is equal to 2, which means your approximation is between 0.5 times the optimal and 2 times the optimal. Somewhere in that range it lies. So இதுக்கு proof இருக்கு. Were you guys taught this proof? I mean, if you were not taught, then I don't want to confuse you with the proof. Can someone tell me if this was taught?
Like
IoT.
little bit of it, like KIDS, kinda like few points were there, and they showed that it's 2 times or something.
Okay, I'll discuss the proof also. So what happens is, let's say you have, let's say your approximation algorithm is choosing k edges, is considering k edges. Okay, va? Over edge ko, 2 vertices are going into the set. So you will have, if T is your set of chosen vertices, T is going to have 2k vertices. Am I correct? Does everyone agree with me on this? Or anything, anyone?
At most 2K, right? At most 2K.
No, நம்ம வந்து நான் அந்த கிராஃப்ல k edges இருக்குன்னு சொல்லல. இந்த algorithm வந்து k edges consider பண்ணுதுன்னு சொல்றேன். So I'm not talking about the edges it deleted. I'm talking about every fresh edge it considers. So every time it considers an edge, it is taking 2 endpoints. So k edges consider பண்ணுச்சுன்னா 2k endpoints வரும்.
Yes.
Exactly 2k. Makes sense. இப்போ where was that graph? இதுல வந்து 1 2 3 4 5 edges இருக்கு. But நம்ம வந்து AB we considered and then CD we considered. AB consider பண்ணும்போது AB ரெண்டுமே தூக்கி அந்த செட்ல போட்டோம். CD consider பண்ணும்போது again C and D தூக்கி உள்ள போட்டோம். So if we consider k edges, we'll have 2k elements in the set. Right?
Yes.
So okay, so my approximate algorithm ல இருந்து எனக்கு கிடைக்கிற solution வந்து k இருக்கு. Now optimal solutionல best caseல நீங்க k edges பாத்தீங்கன்னா for everything if you have one vertex that will be enough. So in the best case your optimal solution will have at least k. Correct. At least yes, we consider k edges in our approximation algorithm. So your graph can have k or more than k edges. So if it has k edges, over edge or one vertex pottingana, there will be k vertices. Or there might be more number of edges in your graph. So your optimal solution will be maximum and the bound for your optimal solution is going to be k less than equal to optimum or optimum greater than equal to k. So t is equal to 2k, optimum equal to k to not complicate things by taking an inequality. If you take this is equal to 2k and this is equal to k, the approximation ratio in the worst case is going to be 2. Make sense?
Yeah.
Okay, this is an example. TSP. Okay, TSP is okay. So yeah, that was one example. Next example, TSP, traveling salesman problem. So இதுக்கு வந்து one approximation algorithm you can do is you start anywhere. At every step, you just go to the whichever city has minimum cost. இப்போ A லந்து the minimum cost neighbor is B. From B, the min cost neighbor is J. From J, the min cost neighbor is C. From C, it is E, and so on and so forth. You continue doing this until you have reached every city. Now, there is no way of quantifying that this will be at most 10 times your optimal, 20 times your optimal. There is no way of quantifying at all because the weights are arbitrary. They change from problem to problem. So, this nearest neighbor heuristic has an unbounded approximation ratio. It could be infinity times worse than your optimal solution, in which case such an approximation algorithm is stupid, right? So we need a better approximation algorithm. So if you take a variant of TSP, which is called the metric TSP, anga we can come up with a better approximation algorithm. So before I go into metric TSP, are there any questions so far?
No.
Okay. So metric TSP என்னதுன்னா it is TSP, but your graph weights are defined in such a way that this triangle inequality holds. So for any pair of cities I to j, the direct distance or the direct cost of going from I to j is less than or equal to the cost of going from I to k and k to j, where k is any intermediate. So this property should be satisfied by every ijk triplet in your graph according to the weights. If that holds, then that is an instance of metric TSP problem. Appo we can come up with an approximation algorithm. So what this algorithm says is, you first construct a minimum spanning tree from your graph. I am sure all of you know what MST is and how to compute prims, Kruskal's, discrete math la படிச்சிருப்பீங்க. And on the minimum spanning tree la, you do a depth first traversal. அதுல இருந்து repeat ஆகிற cities remove பண்ணிட்டு unique cities மட்டும் வச்சுக்கிட்டீங்கன்னா, that is going to be your TSP tour. This again is a solution someone proposed. So don't ask me, இப்படிதான் பண்றோம், why not breadth first, all of that. This is what whoever designed it as. So இது பண்ணீங்கன்னா, you will get a TSP tour. And this tour, you can prove it is worst case it is twice as bad as your optimal cost. இப்போ உங்களோட ஒரு particular in the particular case maybe if your optimal cost is going to be 10 units na, in the algorithm வச்சு கிடைக்கிற cost will be at max 20 units, not more than that. That is what this means. And இது எப்படி prove பண்ணலாம்னா, it's nothing too complicated. First thing is your cost of your minimum spanning tree construct பண்றோம்ல, அதோட cost will be less than equal to the optimal cost. And this property is guaranteed provided this triangle equality satisfies. So that is a given to us. So இதையும் combine பண்ணீங்கன்னா, CM is less than optimal and CAP is less than CM and CM is less than optimal. So CAP is less than twice CM is less than twice optimal. So CAP is less than twice optimal. So this is very straightforward. You can like பொறுமையா உட்கார்ந்து படிச்சீங்கன்னா உங்களுக்கு புரியும், or you can of course get back to me if you have doubts. So the idea basically நான் என்ன சொல்ல வரேன்னா is when you have an approximate algorithm, just random-ஆ நான் இப்படி பண்ணேன் அப்படி பண்ணேன் அப்படி I'll make this choice ன்னு சொல்றது does not make sense. Like in this case, this was more like a greedy algorithm with a bad greedy choice. Correct? That is what this essentially is. So you cannot prove that this answer is going to be in any way close to your final answer. So if you're making an approximation algorithm, you should be able to logically prove that this will be worst case la this many times worse than the optimal solution. So that's the key takeaway. Any questions? Okay, so I guess there are no questions. So approximation algorithms fine.
And this thing, it's both of them are too approximate, but in general it can be anything, right?
Yeah, your alpha can be anything greater than 1.
Okay.
Any other questions on approximation? No? Okay. So shall we move to randomized algorithms, or shall we take a break? This is the last lecture like the last set of slides I have for the day.
Finish it.
Finish it off? Okay. Okay, randomized algorithms. Again, NP-hard problems ku deterministic solutions கண்டுபிடிக்கிறது is difficult. So we are trying to make stupid choices and justify them. That is what randomized algorithm essentially is. So you're going to try to exploit the power of randomness wherever possible. But again, you cannot simply pick out an answer and give it and say this is a randomized algorithm. You have to design algorithms which are likely to be correct and likely to be efficient. So when I say likely, it is like 75% probability of giving you the right answer. So if you run this algorithm 100 times, approximately 75 times you will get the right answer. அந்த மாதிரி ஒரு some mathematical bound or proof or some estimate of how good this is should be given again. So yeah, randomness na enna you know, stupid sorting is trivial, we can ignore that. Quick sort, yeah, we'll look at quick sort. So quick sort, I am pretty sure you all know what quick sort is. So merge sort theriyumla, everyone knows merge sort, right? You learned merge sort and divide. I'm sure you learned merge sort and divide and conquer. So quick sort is basically merge sort, but merge sort la வந்து we'll split in the middle. Correct? Median element pivot வச்சிட்டு left right னு split பண்ணுவோம். Quick sort la the choice of pivot is arbitrary. That is the only difference between a quick sort and merge sort. So இப்போ quick sort is in one sense a randomized algorithm, right? ஏன்னா வந்து your choice of pivot is random, and your merge sort, quick sort lala, your whole time complexity, number of operations depends on your choice of pivot. Where is that slide? Good case, bad case, no. So if you choose the median element as the pivot, then correct half of your array will be on the LHS, half of your array will be on the RHS. It is an equal division of labor. Everything goes smoothly. If your pivot happens to be the greatest or the smallest element, then everything is going to be on one side. It is a lopsided system, so it again becomes O of n kind of layout. So because your choice of pivot is random here, there is a good case and a bad case. So enna nadakundrathu, ultimately you will get the sorted sequence irrespective of what pivot you choose. So answer will be 100% correct 100% of the time, but efficient is a question mark which depends on the choice of pivot. So when efficient is a question mark, you cannot come up with a time complexity. What you have to come up with is expected time complexity, expectation of a random variable. I'm sure you all know from statistics. So இப்போ வந்து again we'll first find the recurrence equation and then அதுக்கு we'll compute the expectation. So the recurrence equation is going to be T of n is T of I plus T of n minus I minus 1 plus n minus 1. I'll tell you how this comes. So I'm choosing the ith element to be the pivot. Okay, wow. So there are going to be I elements on the left side, n minus I minus 1 elements on the right side. So on the left side sort பண்றதுக்கு இது, right side sort பண்றதுக்கு இது. And how did I put those elements on the left and right sides respectively? All the remaining n minus 1 elements in the array, I compared them with this pivot. So greater இருந்தா இந்த பக்கம், less இருந்தா அந்த பக்கம் போட்டு. So n minus 1 comparisons I had to do. So that is one constant operation, constant order term which we will have, which is n minus 1. So this is the recurrence equation. Is this clear? Everyone?
Yes.
Okay. So இப்போ இந்த recurrence equation direct we cannot like you can't do your substitution or tree or whatever for two reasons. One, this depend no two reasons, both being the same actually. It depends on I. So mathematically in the I is an unknown term, so it's not just T of n. So நீங்க ஒரு recurrence tree போட்டு direct பண்ண முடியாது. And logically again, when your value of I is different, your recurrence equation, அதோட bound, everything is going to be different. So we cannot just unscramble the recurrence equation. We have to find the expected time complexity. So expectation of T of n is expectation of n minus 1 plus expectation of this term. இங்க இந்த 1 by n ஏன் multiply ஆகுதுன்னா, expectation is event into probability of event, you know. So here this part T of I plus T of n minus I blah 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 is the event, and the probability of ith number being chosen as pivot is 1 by n for any number. N numbers இருக்கு, any of them can be chosen as pivot with uniform probability, so 1 by n. So this is the expectation formula. Is this clear? Yes, okay, hopefully. So இதுக்கப்புறம் it is just math, algebraic manipulation. So I'm not going to explain the math. You can go through it. Doubts இருந்தா please feel free to get back to me. So now in the summation, we are approximating it to an integration, and then you do the integration. Finally, you will get order of n log n. So the expected time complexity of quicksort is n log n. This is the idea. If you want the integral math, it is also here. So essentially, what am I trying to say? Quicksort is a randomized algorithm. What is random about quicksort? The choice of pivot. So what can I say about the correctness and efficiency of quicksort? Now, enna pivot எடுத்தாலும் ultimately it will give me the correct sorted sequence. So it is 100% going to be correct. Efficiency depends on my choice of pivot. So can I give an expected time complexity bound? Yes, it is order of n log n. How? This mathematical proof tells me how. This is the whole idea. So are we clear so far? Hopefully. So yeah, there are three types of randomized algorithms. Las Vegas algorithms are algorithms which are always correct. If a quicksort pathina, it is always correct. There's something called Monte Carlo algorithms which are probably correct, but they terminate within a time bound. Sherwood algorithms, they are always correct, and worst case scenario, like for example, quicksort and the greatest element pivot choose pandrom. And the many scenarios, Sherwood algorithms work better. They give you a better time complexity. That's the idea. Okay. Yes, we are done. So if you have any doubts, you can get it clarified now. Or if there are any other topics which you want me to like revise or something now, you can ping me. We can have another session in the afternoon also. I don't want to hold you guys back for a long time. It's already been 2 hours.
That 3 sat to vertex cover alone, can you get back?
Jerry, நான் பார்த்துட்டு I'll either like write some notes kind of thing and send, or something. I'll do something about it. Yeah.
Okay,
3 sat to vertex cover.
I mean, that's what's mentioned in some random notes that you have portions for.
Sherry, can someone just put that in our group so that I don't forget? Okay. Also, I'm stopping the recording.